Our next topic is to get an understanding of the voltage standing wave ratio, which has the very catchy abbreviation of VSWR, or VSWR, if you want to sound like you know what you're talking about. And so before we dive into this, let's just say the main purpose of the VSWR is that it's an easy way to measure and figure out what the reflection coefficient is. And by reflection coefficient, I'm referring to the complex reflection coefficient, which can be written in the form of some magnitude and then some phase. Before we dive into the math, let's do a quick demonstration using some very ancient software that was provided to me. So this is a old program that just does some time domain FDTD simulation of the wave propagation down a transmission line, which will give us a good starting point for getting some intuition as to what we're talking about. Let's start by looking at the perfect and worst cases in terms of impedance matching. So let's just start by setting a perfect match at the load. So Z naught is 50 ohms. We'll set the resistive load to be 50 ohms. And we'll start the simulation. So as you can see, the wave is propagating down the line. Once it reaches the load, there's no reflection, so it just keeps going. And if we observe the envelope, you'll see that we just have this constant envelope that is the amplitude of the wave. So in this case, if the amplitude is 1 volt, we just get this 1 volt amplitude here. Now let's take a look at the worst case scenario, which is, let's say, a short circuit match. So we'll set the resistive load to be equal to 0. And now before I start this, I'll just say this is basically what happens when you set this to be 0. That means the voltage is fixed at 0 no matter what happens. So this is the same as if you say tied a piece of string to a doorknob, so you're fixing the location, and then you're swinging it up and down and sending a wave down. So let's see what happens. So the wave comes across merrily, and then it hits this thing that just fixes it at 0. The resulting reflection, which goes back and interferes with the input wave, and then eventually you get a standing wave, which behaves like what you see here. And if you look at the envelope, what the standing wave does. If you look at the envelope, what the standing wave does is you have these periodic maxes and periodic nulls that are completely independent of time. So what happens if you have something that's not a perfect match, but not like a full-on plus or minus 1 reflection? Well, so what you would see is that the portion that transmits through will be a traveling wave, and the portion that reflects will give a standing wave. So you're going to get a combination of a traveling wave and a standing wave. So let's start one more simulation to see what that looks like. So I'm going to take out the envelope. Right now, let's just say we'll set the load to be 50 and 50 for the real and imaginary part. Let's keep going. So this wave comes along. Similar to what you see before, it's going to hit this termination. Now a portion of it will go through and the rest of it will reflect. So this looks a little bit similar to what we were seeing before because where we were looking at the pure reflection place. But if we take a look at the envelope, you'll see that the traveling wave portion takes over where you would otherwise have the null. So the maxes, the maximums still are there, but then you also get this minimum, these nulls that don't go all the way down to 0 because you still have that traveling wave component. And so you can imagine that in the worst case, you have a reflection coefficient of 1, your null is all the way down to 0. And then in between, if you have a perfect match, you have no nulls. It's just that flat envelope that we saw. So if you have a partial reflection, you're going to get these maximums that aren't as big as your perfect reflection, and these nulls that don't go necessarily all the way to 0. Therefore, by examining the relationship between the maximum and the minimum, as well as their placement, you can get an idea and infer what the reflection coefficient is. And this is very useful because quite often, if this is a very fast electromagnetic wave, you don't you can't really always see this propagating along in the time domain nicely like what you see now. But this envelope, that's something that is very easy to detect. You can just measure the voltage and track it as a function of position, which will allow you to trace out the envelope and extract the information that you need. So now that we've kind of seen it, let's dive into some gory equations. For the purposes of this discussion, I don't necessarily want you to be able to derive the whole thing, but I want you to kind of understand the basic procedure of where the equations come from. So let's just say the load is, so we're gonna use a different kind of coordinate system. It's just like what we had before with z, but right now let's just set the origin to be equal to the location of the load. So I'm going to call this the letter u, and u is just like z, except before z equals 0 is over here, we're going to set the origin over here and call that u. So the phasor for a traveling wave, based on our previous discussion, I'll just call this total, as a function of, before we were saying z, now we'll call this u, is going to be equal to v naught, and then you have a positive going component, and then plus your reflection. And your reflection is just going to be your reflection coefficient times v naught e to the j beta u. Now the reflection coefficient is, just to keep in mind, in this case we're looking at a complex reflection coefficient because our impedances can be complex. So the reflection coefficient at the load, still our old expression of nu minus old over nu plus old. But now we should also keep in mind that these are complex numbers, so you can reduce it into a single complex number with a real and imaginary component, or in this case, let's write it in polar form. So we have a magnitude and then an angle associated with this reflection coefficient. So we're going to plug this into our voltage phasor, and then we're going to get something that looks like this. We have v naught e to the minus j beta u plus the magnitude and phase. So the phase can get lumped into this top term here. So we have beta z, beta u, plus phi. And then you can pull, in many cases, when you're trying to simplify something like this, one of the things that you can do is you can factor out, if you have an angle here but not there, you can factor out half of that angle. So we're going to pull that trick and get v naught e to the j phi over 2 of e to the minus j beta u e to the minus j phi over 2 plus gamma of e to the j beta u e to the plus j phi over 2. So a little trick there. That will allow us to do some combining and try to get something that is in the form of a cosine. So with some more clever manipulation that I don't think is worth losing sleep over, I just mostly want you to see what the final cleaned up expression would look like. So I have v naught 1 minus gamma e to the j beta u plus 2 v naught gamma e to the j phi half cosine of beta u plus phi over 2. Now this part is going to be the traveling wave, and this term over here is going to be your standing wave. Now, how do I know that this part is a standing wave? Remember, what we're going to do is we're going to get the instantaneous form by multiplying it by e to the j omega t. When you do that and take the real part, this has an e to the j component. So in the end, you're going to have a cosine that has a t and a u in it. In this case, there's no e to the j something with a u in it. The u is all in this cosine, which is already a real number. And so when you take the instantaneous form, so instantaneous form, so I'll just write that down here. So now, before this was a function of u, now this is a function of both u and t. We're going to multiply by e to the j omega t, and then take everything that's e to the j something and put it in a cosine, in not so many words. So you're going to have the traveling wave component, cosine of omega t minus beta u. So this is something that looks somewhat familiar. And then separately, you're going to have 2 v naught of gamma. You're going to have this cosine of beta u plus phi over 2, and cosine of omega t plus phi over 2. And this part is a standing wave. And here we can see it's a standing wave because over here, if you choose a location of u such that this term is equal to 0, it's going to be 0 for all time, right? There is nothing that this omega t term can do to make this not 0. And so that means that you're going to have nulls, and that's why this represents a standing wave. In contrast, a traveling wave, you have this interplay between t and u, where adjustments in t can change what the overall thing inside the cosine is for a fixed location of u. And so you can see there's a traveling wave term and a standing wave term, and the amplitudes of the two form the ratio. With this bit of intuition, you can then get a feel for what the envelope's going to look like, and use that to graphically figure out what the VSWR is. So here is this is your U. This is the measured voltage envelope, and we're going to center this. We're just going to look at the upper half of the envelope that you see here. So you're going to see, just like what we saw before, it's going to go up and down and up and down. And a few things to note is that the spacing between them is going to be lambda over 2. The location of the min is going to be equal to minus 1 over 2 beta of phi plus 2m plus 1 of pi. So that's a quick way to figure out where the location of the minima are. And m is all the natural numbers. So it goes 0, 1, 2, and so on and so forth. The maximum is going to be equal to minus 1 over 2 beta of phi plus 2m pi. So using this, you can figure out what the maximum and minima are. And then the value of the max and min, if you take a look at this, the maximum is going to be equal to 1 plus the absolute value of gamma v naught, and the minimum is going to be 1 minus the absolute value of gamma of v naught. In other words, the minima is where the standing wave is at a null, so you just have this amplitude here. And the maxima is when the standing wave is at its max, so you have v naught minus gamma v naught, but then you have this extra 2 v naught up there, so you get the 1 plus gamma v naught. And therefore, the voltage standing wave ratio, which we'll use the letter S, is the maximum over the minimum. It's the standing wave ratio. And so that is going to be equal to 1 plus gamma and 1 minus gamma. Therefore, if you were able to take a really good high resolution measurement of the envelope, the voltage envelope, as a function of position, and compare the two, you can get your VSWR, and then from your VSWR, using this relationship, you can then solve for what gamma is. Now remember, gamma ranges from plus or minus 1, plus and minus 1 being the open circuit and short circuit. And so if you look at the range of what the VSWR can be, it can range from 1, which is a perfect match where the reflection is equal to 0, so that's a perfect match. Or it goes all the way up to infinity, where in the case of infinity, you have a reflection coefficient of 1, which makes the denominator 1. And so So that is going to be an open or short. So basically the worst case when it comes to wanting a match. And so usually this VSWR, you want it to be as close to 1 as possible, and then the bigger it is, the more of a mismatch issue you have. And so this is usually a parameter that you'll often see in data sheets. And again, the main thing that you want to know is it gives you an idea for what kind of reflected power you should expect when you add in, say, a connector or piece two different components together. Oh, and one final thing to note is that since the maximum and the minimum is determined by the amplitude of the standing wave, you can then use this term to figure out the exact location of these maxes and mins. So you can use this to figure out where the location of the first max and min are, and then using these two formula here, you can kind of identify where the location of the other maxes and mins are, and then you draw this curvy envelope, and the max and min would be determined by 1 plus gamma or 1 minus gamma times V naught, and using that you can find the VSWR.